Okay, so kind of following the hurricane theme, I'm going to talk about the coupled benthic and pelagic processes that impact during a hurricane. So remember, these are all shallow shelf. We are talking about the same area in the shallow Gulf of Mexico, Gulf of America. Uh, sediments where we're talking about 10 to 50-meter water depth. I owe a lot to this group. Some of them are actually here. Okil is here. They went out when I couldn't, and it was not even part of their thesis. So thanks, Okil. Thanks, Byron. They really helped me out on this cruise. So when are we going to talk about this? Is we're going to go back to these suite of hurricanes that happened way back in 2017. We had the Hurricane Harvey back in 2017, and then shortly after that, there was Hurricane Nate right here. So what happened after the Hurricane Harvey? We were actually able to get an NSF rapid funding to go out and look at what happens to the water column in response to these hurricanes. So our working hypothesis is we will get a lot of sediment remobilization, and that should impact both the photosynthesis and the respiration, and that should translate to water column changes in the biogeochemistry. So with that, we went out, we collected all the samples. These red dots represents all these samples we collected, all the core samples we collected, and then we used beryllium-7 to figure out what is the net sediment that was recently deposited. So beryllium-7 is a really good tracker. It has a 50 days half-life. So whenever you see beryllium, that is the amount of sediment that was deposited in the past couple of months. And that's what we used to look at the depth of sediment that was deposited. The circle shows us the bigger the size, the bigger is the depth. And we can see at some places, which is far away from the track of the hurricane, we have quite a bit of sediment remobilization that happened. This could be new sediment. This could be sediment that was remobilized into the water column and slowly sank back up to 10 centimeters. So that's a lot of sediment, and in one hurricane event. And when you think about the regular sedimentation rate in this area, we're talking about 0.5 mil. That's it, 0.5 mil a day. Here we have 10 centimeters in a month or so. So that tells us that a huge amount of sediment across the shelf was remobilized and redeposited. And what does the sediment has? It has a lot of particulate carbon, as we know. And in this area, the particulate carbon concentration is about 0.5%. So when we start thinking about that, we can start thinking about how much sediment. So if we do just a back of the envelope calculation for this area up to 40-meter isopath, 50-meter isopath, we see that at the average rate of about 4 centimeter sediment that got stored up, we are mobilizing 8 times 10 to the power 8 metric ton of sediment in the shelf area, which is very comparable to the entire Mississippi Atchafalaya River load that brings in sediment to this area for the whole year. So that's one event that is doing that. And if we translate that to the carbon, that is about this much particulate carbon from the sediment that got ejected into the water column. So now we have a coupled system. We have a storm go through that start up the water, that start up the sediment, and that ejected the sediment into the water column along with the carbon. So what happens to that carbon once it gets ejected to the sediment or once it gets exposed to this new fresh oxygen? So this is actually pre-hurricane Harvey. And we can see we did some core incubation to look at organic matter mineralization rate. So DIC, dissolved inorganic carbon flux, from the sediments tells us how much organic matter mineralization is happening, about 4 millimole per meter square per day. Right after hurricane, bumped up 3 times. So that's the sediment that was remobilized, redeposited, and now it's getting respired at a faster rate. So 15. And then again, when we went out in October, completely unplanned, we got actually stuck in this hurricane. It went up by 5-fold compared to non-hurricane event. So that's the first thing that comes out is like, when we have a hurricane, definitely the bottom sediments, you have a lot of more organic matter that gets exposed. This fresh organic matter gets remobilized really fast. Okay, that's our sediment. What happens to overlying water column when we have these sediment respiration processes picking up? So in the water column, as we can imagine, so these are all the spots where we did water column photosynthesis and respiration. So these dots shows us the photosynthesis, and dark is our respiration. Again, before hurricane in July, photosynthesis to respiration ratio greater than 1, which means photosynthesis more than 1 in the water column in this area. Right after hurricane, P to R ratio less than 1, which means the respiration in the water column actually is higher than photosynthesis, which we start thinking actually starts making sense. Because what did we do with these sediments? We picked them up, put them in the water column, means we reduce the light, reduce the photosynthesis. At the same time, we added the carbon in the water column, which increased the respiration. So not only do we see respiration going up in the sediment, we see the same thing happen in the water column. And again, after the hurricane net, same thing happened. So two things. The hurricane picked up the respiration in the sediment. It also translated to higher respiration rate in the water column. And we did have a oxygen sensor at C6, and this is really cool. So if we start thinking about it, when we have a storm, we have bottom oxygen in this area, which is really low. The storm should mix it up, reoxygenate the water. But the question is, how long does it reoxygenate the water? We always thought that whenever there is a storm, it is good for hypoxia because you're breaking that hypoxia by injecting oxygen. But what this figure shows here is driven by this increased respiration that we saw both in the sediment and in the water column. Although after every storm, oxygen does spike up in the bottom, but it also goes back very quickly, which is really neat because we did not expect that. We expected the oxygen to be reoxygenated in the bottom water for a longer time, but it doesn't stay there. So that means we really have to rethink how long, what is the duration of this effect that happens from the hurricane. That is one data that we see. The dotted lines here is actually from a model output, and this is real oxygen data that we're seeing. It goes up after a storm, but very quickly goes down. So what does that all mean? So the net effect that we saw is we see a lot more CO2 produced, right? Because overall, I kind of showed we have higher photosynthesis, higher respiration in the sediment, higher respiration in the water column, which means higher CO2 production. Sure enough. Again, here if we see before the tiny hurricane, shown here in green, CO2 concentration in the water column, post-hurricane went up by almost 100 ppm in the water column. And what does that translate to pH? We can see the pH drop just after this tiny storm that happened, 0.1 unit. And that 0.1 unit, that's ocean acidification for the last 100 years, to put things in perspective. So we now see how things are getting connected. You have a hurricane, you have enhanced respiration rate, you increase the CO2 flux into the system, and that can drop pH. It also means that we're transferring the carbon, which would have otherwise been actually being saved and into the sediment and sequestered, can actually be injected back into the water column, which it can produce CO2 and flux out into the atmosphere. So we have multiple effects that can happen from this hurricane, and that can also lead to this temporary pH drop. We don't know how long this pH drop is sustained, but it does happen immediately after a storm. And we see the same thing. We just compared some of these really high CO2 that we measured at the surface water after the hurricane, compared them with some old data, non-hurricane year. We can see right here, the CO2 concentration in the surface is 600, 700, 800 ppm, whereas under normal conditions, it's more in the range of 400, which is what we expect. That difference must be going into the atmosphere. So not only does it translate carbon transfer from sediment to water column, but it can also increase carbon transport or CO2 transfer from water column to the atmosphere. So that's how the hurricane cycle probably impacts all the interfaces in a shallow shelf. And so I think I'm doing pretty good on time. Nobody's bothering me, so I think I'm good. So what we can kind of take home from this, massive amount of sediments get mobilized. It increases respiration rate. DIC fluxes from the sediments goes up, water column CO2 production goes up, drops pH. Hypoxia, although it very quickly disappears, but it comes back pretty quickly too. But it didn't answer all our questions. We didn't really know how long this system actually stays in this post-hurricane system. What is the connection between the land and the ocean? What about the estuaries? How does it get impacted by these hurricane events? So with those questions, we actually went out and we got our NASA funding to look at all these processes about the time scale and the resiliency of the system. And guess what? After 2021, we really didn't get much hurricane. So we got a project funded, but we don't have a hurricane. So we are hoping a tiny category 1 hurricane, maybe for this year. This is our last year of project. And that is me actually watching my lander, the first picture I showed you, breaking right apart in front of me. And I'm trying to make sure I don't wash off. Okay, thank you all.